Can you hear me?
Yes, we can hear you.
Yes, sir.
Okay. So let us start. Is it visible?
Yes, sir.
Yes, sir.
Okay. So, Professor Mitro has mentioned, we will be discussing, we need to discuss the runtime environment for a program, because that plays a key role in terms of how do we actually compile the program, particularly towards the back end. And that in turn decides what information we gather and how we organize them in the front end. Right. Now, in terms of our theory discussions, this comes certainly closer to the back end, actually at the transition of front end and back end. But by that time we can reach there, it will be quite late for our laboratory pursuits. So we will start discussing it here. And over I think 2 or 3 days, we will try to cover this. So our objective in this entire module is to understand the runtime environment for program execution, which involves primarily the understanding of symbol table and activation record or stack frame, and what is their interrelationships. One is at a compile time, one is at a runtime, but how are they interrelated? And we do that through the understanding of binding, layout, and translation of various data types and various types of scopes that the program has. So this is the overall outline. Let us get focused on these few, which is particularly required for our laboratory purpose. Okay, now the core question that we have to address, besides lexical analysis, parsing, semantics, and all that, is how do we manage the symbols that exist in our program? Symbols typically mean variables that we use for expressing different computations. There could be special type of variables which we call parameters, formal as well as actual parameters. There could be unnamed temporaries, which are variables but which the programmer did not write, but the compiler has to write to break down a complex expression in terms of 3 address codes and so on. Symbols are defined in terms of their scope, blocks, as you know, and same lexical name. Suppose I have used a symbol called count. The same lexical name may be used in different scopes, actually meaning different variables. Function names are also symbols. Symbols could be local, symbols could be global. So symbols need a very extensive management. And in a way, besides the whole of the translation process, the different phases revolve around how do we collect information about the symbols in a program and how do we manage them, right? Now, in this connection, let me introduce you, not introduce, you already know, but reiterate 4 terminology related to symbols. One is we say a symbol is declared, or more commonly we say a variable is declared. So I write int x, that is a declaration for x. So what do I get to know about that symbol through a declaration? I get to know that, well, the name of the symbol is x. 2, that it is of type int. So once I know it is of type int, I know a whole lot more about the symbol, like what should be its size, what is the range of data it can represent, what are the operations I can do with it, and so on and so forth. And the third is by the lexical position of where I have written int x, I know the scope in which the symbol is defined. It could be within a function. It could be outside of any function. We say these are global declarations. It could be within nested blocks in a function, which we'll say are nested scope symbols. Could be as a parameter on function header, and so on. Right? So a declaration tells us about typically the name of the symbol and its type. Now the second thing that we use is I can write int x equal to symbol, or which looks like assignment symbol. Int x is equal to 10. This should be read as an initialization. This is not assignment. This is obviously not equality comparison. So when I say int x initialize 10, I call that as an initialization of the symbol. So what it means is whenever that symbol comes into effect during execution, when the control flow reaches that declaration point, then along with the declaration information, I know that initially the value of that symbol will have to be the particular initialization value that I have used. Depending on context, initialization could be by a constant or could be by another variable. So this is what we will call initialization. So we have declaration, we have initialization. Then the third is I can make an assignment to a variable. Right? I say x assigned 5, semicolon. This is an assignment expression. With semicolon, this becomes an assignment statement. And this is an assignment which will erase the existing value of the symbol x and put a new value. So that is a write operation. Right? It is different from initialization, which is not typically a write operation. So do not confuse between initialization and definition. This is called a definition. A definition is where the variable is getting, or the symbol is getting, a new value. That new value may not necessarily be distinct from its current value, but whenever it gets a new value, typically by an assignment, or it could get by an indirect assignment also, and so on. Whenever it gets that, we say it is a definition of the symbol. So do not confuse between declaration and definition. Declaration is merely saying that this is the name and this is the type. Initialization says that whenever the control reaches there, this is the value that the symbol should have, and it is optional, as you know. And any definition will perform a write operation, changing the current value of the symbol to a new value. So these are the three. The fourth about a symbol is its binding. That is, while the program executes, when the control reaches the declaration, and subsequently till the time the control is within the scope where the symbol is defined, during this time, the variable must have a memory address, right? You know that everything is remembered in terms of memory locations. So the correspondence between the symbol name or the symbol and its address in the memory is called the binding. It's called memory binding, physical binding, different ways, but it is binding, right? So we know that for most symbols in C, we can use an address of operator to get the address. So if int x is a declaration, then ampersand x is the binding of x at the runtime. So if we think about these four and be very clear about what these terms mean, do not use any one of the term in the context of the other. Do not call an assignment as an initialization or an initialization as a definition. No. A declaration, initialization, definition, and binding are the four terms to be associated with any symbol. For example, when we provide a function with just the prototype, not the body, then what is that? That is a function declaration, right? Because you are not specifying what the function does. You are just specifying that I have a function Fibonacci, which takes an integer n and computes the Fibonacci number. That is the intended semantics, that leave that aside. But you're saying that Fibonacci is a function which takes an integer, gives me an integer, right? Even the name of the formal parameter is just a placeholder. So when you say that, that is what we say is a function header or the prototype. When you say that, you are actually declaring a function. And what is the definition of a function?
Excuse me, sir.
Yes.
So your slides are frozen on page number 06.5 for like, they've been frozen for...
I have not moved slides.
Oh, okay, sir.
I have not moved slides. When I move slides, I'll say that next slide.
All right.
So because I did not make slides for this, because as it is, you will know these things. Yeah. But I just wanted to be very clear about the language that we are going to use so that there is no confusion. When I say definition, you should not think it is a declaration. Yes. Right? Yes. So I'm just reiterating those points.
Yes, sir.
I'll come to this slide. I'm reiterating those points to come to this slide. I have not yet started on this slide. Okay.
I'm sorry, sir. Yeah.
No. Welcome. Always ask questions, because that keeps me going. That I know that yes, at least somebody is listening to me. I'm not talking to the wall. Otherwise, in front of it, I have a yellow wall. That's it. So frustrating. Okay. Now, so when I say I have a function header, int Fibo int, I know this is a function symbol. The type is a mapping from integer to integer, and therefore it is just a declaration. When I write the body, it becomes a definition. Since functions can have only one definition in C, there is no concept of any separate initialization or separate definition for a function. As you know, there can be several declarations of the same function, but only one definition, right? So these are the basic. Now let us see that looking from the compiler's perspective, what is that we have and what is that we need? When I'm compiling, I'm not actually running the program, right? So there is no runtime. The program is all in text, and I just have the symbols and the expressions in the program. So while I compile a declaration, I will get to know what is the symbol name and what is its type. You have already studied about lexical analyzer, which will lexically separate them out. How do you say that X is a valid symbol and int is a valid type is a question of syntax and semantic analysis that will come later on. But the information that I get from this is X is a symbol and int is type. I will use the symbol table to remember this information. I do not know more about this yet. but I have come to know that X is a symbol. Lexical analysis tells me X is a symbol. Syntax analysis will tell me that int is a type. I will keep on writing this information on the symbol table. I'll create a table and keep on writing them. Right? So write that in the symbol table, that its type is int, the name is X, initialization is with 10. But what I cannot write, cannot know at the compile time, and therefore cannot have it in the symbol table is a fact. What is its binding? Because binding is the physical memory address, and I do not have that at compile time. So I have to do some trick so that when the program actually runs, I'll be able to get the binding as long as the program runs. And when the program gets over, the binding is also over. Actually, I should be more precise. It is not about the entire program. According to the structure followed in C, C++, Java, and most of the programming languages, the majority of binding is created on a function basis. So when I start executing a function, it is called from somebody. Then all symbols that are associated with that function, the parameters, the local variables, the temporary, and all variables which occur in the nested block within that function come into existence. And interestingly, I do not wait for a nested block to come into execution for binding its memory. I actually bind the memory for all symbols within a function at the same time. So from the symbol table, I collect all that information of what the symbols are and create their necessary binding. This is the role of the symbol table. So that is what you get to see at the compile time. Now let us go to the right-hand side column. I'm currently discussing slide 6.5. I have other concept called activation record. Some literature call it stack frame, interchangeably. In the activation record, it is a layout in memory at the runtime. So it is in the basis of target code. It is basically a layout. So it is a segment of memory. It is a section of memory, consecutive bytes in memory, which is considered to be a record for the particular function which is currently executing. So what do you have? At runtime, what will you have? You'll only have data. So you have addresses for the memory locations. You have contents for the memory location. Naturally, you will not have symbols. Naturally, you will not have types. Naturally, you will not have initialization. But whenever you get a definition of the control crosses the definition of a variable, the corresponding bound address memory location must get written with that value. Right? So if I look into what are the things that the activation record must have, and mind you, they must have all these. Activation record must have all these without any reference to the name of the symbol or its type or anything. It has to be a layout which implicitly tells me everything. Right? That's the challenge. Because as in compile time, I do not know the physical address. As in runtime, I do not know the front-end information of symbol names and types and all that. All that are got consumed by the compiler. Right? So the activation record will also have variables, memory locations designated for variables, including parameters, local variables, temporaries, and further there may be some non-local references. For example, I'm referring to a global variable. So I will also need to have that address reference. But that is not enough. the activation record also needs certain management data to be written. For example, if main calls function Fibonacci, from the point main has called, after Fibonacci finishes computation, the control has to come back to that same point. Okay? So would it come back to the same point? So at the time of call of Fibonacci from main, somehow I have to remember that return address from where the call had been initiated, or more specifically, the address after that call where on return from Fibonacci, the control must go. So I must have the return address. I'm computing a function, so naturally I will have a return value. Forgetting about the case of void return. In addition, I must have saved machine status. This question came up in some of the earlier discussions from you as to what happens to the registers, because the same set of registers are used and reused by different functions. So the registers that main was using, the same registers are used by Fibonacci when I call it. But when Fibonacci returns to main, I must get the old values of those registers back, even though during execution, Fibonacci was actually using those registers. So there's a concept of saved machine status. And then finally, the activation record has to, would you please mute yourself, whoever it is, please mute yourself. Noise is coming, please mute. Finally, also we will need to keep information in the activation record in terms of all these binding and putting of return address, saving machine status, restoring machine status. Who is going to do what? Now, what do I mean by who is going to do what? Who are the people? There are two people involved. One is the function which is making the call. We call the caller. And the function that is being called, we call it a callee. So if main calls Fibonacci, main is the caller, Fibonacci is the callee. So all this management has to happen either by main or by Fibonacci, but they must happen in a certain handshaking mode so that everything falls in place. So that's the scope of the activation record. And symbol table at the compile time, but this interconnect between the symbol table and the activation record is a critical thing. And that is what we are going to understand now. I'm going to the next slide, 6.6. I hope you can see it. First, since you have not done symbol table as yet, first let me walk you through an example to make you understand what a symbol table actually is. So I have a very simple C function on left, two functions, a program, a function add which takes two integers and adds them and returns that value, and a function main which takes the usual parameters and does not initialize anything, declares three variables A, B, C. First has two definitions for A and B, then it calls the function add with these parameters A, B, and defines C with the return value of add A, B. Now, if I write this in terms of three address code, which in the introductory lecture I mentioned that these are very simple statements, constraining that every statement, every code has at most three addresses. Then what do I need to do? I first need to add X with Y. So I add X with Y. I'm in the first line on the right-hand side column. I add X with Y and put it to a temporary T1. The T1 is a machine-generated temporary, compiler-generated temporary. Right? You would question as to why am I doing that? Why not I put X plus Y directly into Z? These reasons will be understood better when you do syntax analysis. The main reason is when you see X plus Y, you are not aware what is going to be done with X plus Y, whether there will be another, after this there may be another another addition which you have to do, or there may be a subtraction following this and so on. You do not know all of that. So you simply put it, this sub expression x plus y as a temporary t1. Then you have z assigned. So you assign t1 to z. You are done. So you return z. So this is a simple 3-address translation of add. Now here you do not say what is x, what is y, where the parameter is coming from. These are supposed to be implicitly known. We will see how. Coming to main, in a similar way, I have to define a with 2, assign 2 to a. So I define another temporary t1. Main is a separate function. So compiler deals with it separately. So it can reuse the same temporary name as it has used in add, because it does not know. When it is compiling main, it does not know about add. So it again uses t1, and that will not clash, we will see. T1 gets 2, A gets T1, T2 gets 3, B gets T2. So 2 temporary is used. And then you have to make the call. The call mechanism in 3-address is very simple. You, as many parameters as you have, you put each one of them by a param statement. Param A, param B says that you have parameter A, parameter B, and then you have a call statement which simply has the name of the function and the number of parameters it has. So what it does, when it sees add, it knows that it has to call function add with 2 parameters. So it goes backwards from this point, picks up param A and param B as the parameters and would call A. This is the semantics of the 3-address code. And the result will come to C, then you return. Now let us see what is the symbol table information. First, let us start with the simpler one, which is add. So what are the symbols involved? You can see here, x and y are parameters. So I write in st.add, which I say is as if the symbol table for add. It is a representative one. The name of the symbol, these are on right column bottom, you'll see the explanation of the columns of the symbol table. Name, followed by type, followed by category, size, and offset. So we say name is y, type is int, category is param. That is whether it's a variable, parameter, or a local, etc. You write here. Then its size is 4. Okay. Do not think about this +8 as of now. Then you have x, which is also int, a parameter, size is 4, assuming that it's a 4-byte integer. Z similarly, but for Z, the category is local because it is not a parameter. It is defined, it is declared as a local variable. That is 4. And T1 is a symbol that you have generated, which is also of type int. So you say it is category temp, size is 4. Right? Now, let us talk about function symbol table for function main. It is in the same way, 2 parameters. The first, you can see that for some reason, we are processing the parameters from right to left. You can process them from left to right also. But I mean, many systems process them from right to left. Again, the reason is hidden in terms of the way the translation is done by the syntax analyzer. You'll get to see that. But do not worry about this order. Any order is fine. So if I follow that right to left order, then my first parameter is argv. Now, what is argv? Argv is an array of type char star. So I say array, type is char star. Within array, this is an array type. Right? We are talking about a type. What type is argv? It is an array type. What is the array element? What is specified here? Char star. How many elements are there in the array? Usually, if I have int a 10, I will say it is array 10 int. Number of elements followed by the type. Here, the type of the element is char star, and here we have a blank in the size, which is specifically allowed in such contexts, which say that it is an unbounded array. So I specify that by putting star. Category is param, size is 4. Why is the size 4? Because an array is equivalent to its base address, which means that it is a pointer. And I'm assuming that the pointer in this system has a 4-byte address. Next, I have argc, which is of type int. Then it is also param, size 4. I have three declarations of local variables, ABC, int, local. And in the translation, I have used 2 temporary variables, T1, T2. They come after that, int, temp. Suppose this is the symbol table organizer. The real symbol table will look a lot more complex than this. But I'm giving a simplified view to get started with. Where do I get my information for the activation record? Right? So this is a symbol table that you will have for the main. Right? Now, besides these 2 symbol tables, you will also have another symbol table which every program has. It's called the global symbol table, which means that any symbol that you declare outside of any function scope, right? Anything that you declare. So that is a global symbol table. You are familiar with global scope. So every symbol table represents a scope. Add symbol table and main symbol table represents a function scope of the corresponding functions. Whereas global is a special symbol table which will always be there, which just has entries for the global symbols. So what are the global symbols in this program? There are 2 global symbols. That is the 2 functions that have been put in this program. So I have a function int, that is the name of the symbol. What is the type? The type is a function. So it takes a pair of integer. So I say integer cross integer, which means a cross product, which means any pair of integer, doublet of integers can go in. And what I get as a result, the range of that function is, or codomain of the function is int. It gives me an int. Category is function. Naturally, it is a function declaration, so it does not as such take any space. So I say that the size is 0. When it comes to main, it is a little bit more complicated. Your first argument is of int type. Second, argv, you have already seen in the symbol table of main that it is an array type of elements cat star having unbounded number of elements. So cross product of these and the result is a void. Category is function, size is 0. Right? So this is the basic. And there are in actual symbol table there are other information like symbol st add and st main are treated as children of st global, because the whole scope of global subsumes the scope of main and scope of add. So I can look at them as a tree also, with global being the root and st.add and st.main being its 2 children. And therefore, I can also have parent links going from add to st.add to st.global or st.main to st.global. Those are finer details. Now we want to understand the last column, which is what basically links symbol tables with activation record. What I say is, if these are the symbols, let's talk about symbol table of add. If these are the symbols, then as if while I get into execution in memory, I will allocate the memory one after the other. So there'll be Y, then X, then Z, then T1, and so on. Then all these 4 together becomes my activation record. The question is, in the activation record, I do not have the symbol. So how do I get to know which variable is what? So I use the concept of, one second. There's some nagging call coming. So I'm sorry. So I do not, at the activation record, I will not have that information. So what I do is something interesting, is what I put here are called offsets. That is as if there is a pointer which holds this entire activation record of a function, and that points somewhere. Let's say that points at Z. And then I see, going away from that pointer, how many bytes I have to go away to get the next symbol. So it says at 0, wherever that pointer is, I will get Z. If I go 4 bytes away on this side, I will get X plus 4. If I go another 4 bytes away in Y, I will get plus 8, which is Y. On the other side, if I go 4 bytes away, I will get T1. You can see the same thing in symbol table of main. In the offset, A is 0, B is -4, C is -8. So all that I'm doing is basically, if you look at the size here, all of them have 4, but on one side, I have a 0, which is the kind of the holding pointer of this activation record. And I have offsets on both sides, showing where my symbols are expected. How does that help? Now, in the function x, the function add, if I have to talk about x, I will not talk about x. I will talk about a base pointer plus 4. If I call this the base pointer of the activation record, or more specifically coming to your processor register terminology, if I say that EBP has this pointer, then I'll say wherever I have x, it is actually EBP plus 4. Wherever it has y, it is actually EBP plus 8. Wherever it has z, it is actually EBP plus 0. Wherever it has T1, it is EBP minus 4, and so on. So whatever was a name in the symbol table in front end becomes an address expression in terms of my activation record. And all of these are in terms of the offset. So the only unknown in that address, which comes from the runtime, is the value of the EBP, the extended base pointer register. So wherever you give me memory, anywhere, any physical address, once I can set the value to EBP, I will have actual physical address to all symbols from this address expression. And that is what is called the binding. Right? So before I continue, let me stop and go back to you for a while, because I have bombarded you with a lot of concepts together in one slide. If there are questions, let me take that. Otherwise, I'll go more deeper into the activation record.
Sir, for the function parameters being passed, are we like assigning the offsets right now? Because it is not necessary that we want to pass the parameters on the stack. We can pass it via registers as well. So since you're referring to everything with respect to the base pointer.
Deep. Let us not jump the cart. So let us go from simple to complex. Are you getting me? What you can do always is pass it on stack. Exceptions are that you may pass something on register. Right? So let us first understand the uniform mechanism. Then we will come into the optimizing mechanisms. Are you getting me? What you're saying is correct. I understand that you know, but may not be so for everyone here. And we have to go from a general scheme and then talk about exceptions or optimizations to improve on that scheme. If we start with a complex scheme that actually finally turns out to be, then we will not be able to understand it. Got it?
Yes, sir.
Any other question?
Sir, am I audible?
Yes.
So how are you allocating the offset for T1 and all the rest of variables? Like, why is it T1 -4 and not +4? Like,
It's my wish. You can do it any other way. But two basic constraints, Yashika. One is I want to make them consecutive, do not waste space. Two is I am going to make some protocol so that when a function is called, the caller and the callee will both know enough to manage the part of information that they have to share. For example, at the time of call, the actual parameters will have to be copied for formal parameters, right?
yes.
Actual parameters are local variables or parameters or temporaries in the calling function.
Yes.
And the formal parameters where you're passing are parameters in the called function. These will be in two different activation records. So a function knows its own activation record. Other function knows its own activation record. How are they going to handshake between them? So there are some protocols that I have to cling to so that any function, even without knowing the activation record of another function, would be able to pass the parameters. Any function without knowing the details of the caller would be able to give the return value back, right? So we will see why are they like this, why 0 is in the middle, why some side is positive, some side is negative. The details will come to that. We'll take examples, slowly it will become clear. But you can also assume that 0 is at one end and everything is increasing or everything is decreasing, does not matter. Only thing is your calling return protocol becomes more complicated. That is the experience. So if you see, we are trying to kind of separate out things that parameters are on one side and keep the others on the other side and so on and so forth, right?
Yes. So like the return type, I thought was basically the zeroth one.
We will see. We will see. I mean, this is, see, the symbol table, mind you, symbol table is dealing with symbols, right?
Yes.
Now in C, I'm not talking about Pascal, which had explicit output parameters. But in C, the return value does not have a name, right? The return value does not have a name. There's no symbol for the return value. It is synonymous with the name of the function. But the function is a different entity. And it does not have a memory allocation because it's a computation, right? So symbol table does not have an entry for a return address because there is no symbol for it. What would you enter? But activation record must have. Otherwise, from the activation record of one function, you will not be able to give it to the other function. Similarly, the questions of how do I go back? The return address will not be there in the symbol table, but it has to be there in the activation record. So these details are there. All that I'm trying to make a point about in this part is the fact that symbol table maps symbols to certain address expressions which are offsets, ensuring consecutivity of all the symbols. And the offsets are such that if I have a base pointer value, I can add the offset and I will do the binding of the corresponding symbol at that value. So that the activation record does not need to remember which was X. To the activation record, it is base pointer plus the offset of X. That's it. And that offset is constant. Right? That is the translation mechanism. Is it making sense?
Yes, sir. Yes.
And any other question?
Sir, you said there should be continuity while assigning the offset, right?
Yes,
So,
yes.
so what do you exactly mean by continuity? Like, I cannot leave any space.
Yes, you would not like to, right? That will be wastage.
What if the data size is such that you have to leave some space?
Why do you have to leave space? First, you tell me. That, if you leave some gap in between,
Yeah.
then what will be used for? It's just a wastage.
I thought there might be some situations where we have to, but I can't think of that.
I will tell you the situations when the point comes. What you are thinking is not out of the blue, but again, as I was reacting to Deep, the question is, we do not start with all those complications. For example, there is a scheme to introduce empty spaces around every variable on both sides, just to see that you are not overrunning an address. Right? You are traversing by pointer, and if you overrun, then it will hit a certain location which is not allocated to anyone. So you will immediately know. So there are schemes, debugging schemes like that. There are certain mechanisms of runtime edit of the code. Particularly if you have, I'm not very familiar of this feature in GDB. Pralay would know better. But if you are working in Visual Studio, there's an option that while you are in execution, you can edit some code and continue executing without stopping it and recompiling the program. So it is managed by keeping some empty space where you can have a couple of small number of additional variables defined at the front end in the runtime. These are all complicated things. And then we are talking about C or those kind of languages primarily in our mind. But there are several languages. There are interpretive languages. There are variable length data type languages. So do not take it as cast in stone that activation record will always have to be packed neck to neck. But that is the first objective. 90% of designs will cater to that. Rest are exceptions. These are not the general. Getting that?
Yes.
And any other question, anybody?
Sir, you mentioned about like variable length data type. Like, is it possible to have variable length data type at Python and have a compiled language at the same time?
Python is a compiled language.
Yeah, but it's not compiled in the technique. I mean, in the sense of CD.
In the runtime sense. In the runtime sense.
Yeah, it has a runtime and it runs a byte code or whatever.
But I mean, you don't have to jump to Python. We will come to those kind of languages because the idiosyncrasies are different. Before you understand the translation of one language thoroughly, it's better not to talk of a lot of diversions. But variable length data type exists in C++. You have variable length array. It's a valid type now. In C++11, a variable length array is a valid type. Right. So there are certain management issues with that. But again, the question is that what we intend to do is to learn the baseline first. And my baseline language has only only few types. It has int, it has bool, because without that you cannot have control flow, and it has one-dimensional array, nothing else. See, this has two advantages. Yes.
Sir, you said that int I equal to 1, or did I interrupt you?
No, you say, I'll continue then.
So int I equal to 1 you mentioned is initialization, but if I say int I and then semicolon and say I equal to 1, that is declaration then definition.
Yes.
So they're not the same thing.
Yeah, they're not the same thing because for I assign 1 semicolon, you have to actually do an explicit write.
Yes.
And for I assigned int I initialized 1, when you allocate the activation record at that time itself, you fill up that memory. You do not do a separate write. So these two are two different things.
Even in C.
Initialization is something which is computable to a good extent at the static time. Assignments are not, definitions are not.
Okay.
So it is important to see the difference because will also come severely in the discussion when we deal from syntax to semantic translation. Syntax is similar here, but the semantics is very different. In one semantics, in initialization, the initializing value must go in the symbol table, otherwise you will not remember it. It is not there in the program code. Whereas for an assignment definition or some other definition, you don't have to put it to the symbol table because there could be several of them, and wherever they come, they will feature. Right? So there is a significant semantic difference in spite of the syntactic similarity. And just to say forward, because some of you may be familiar, if you come to C++ 11 onwards, you will see that a separate syntax of curly braces is being emphasized for initialization alone, so that even the syntax can differentiate the semantics of what is initialization from what is a definition. Right? But those are advanced points. I just want to stick to the code that my language, as I was saying, has three things: integer type, bool type, and one-dimensional array type, nothing else. Now, why so? For two reasons. One is that every language has this. You cannot think of a language which does not have these three. Two is, with this you can write any kind of program. So this is the simplest model to use for learning the compiler. And then once you learn it in terms of these three, then you can easily start learning for different data types. How are they different from int? Tells you how to handle float, how to handle double, so on and so forth. And it becomes easier to comprehend the whole thing, because otherwise the whole general system is so complex to start with that unless you take a top-down approach to break down the complexity, you will get lost in the whole thing. You can just see that we just introduced, Professor Mitro just introduced very basic things about the organization of the CPU and registers, memory addressing, and so on, with the assembly language. And some of you have been complaining that it's too much. I understand it is too much because things are complex, and you're talking about the core of the machine and the core of the things. Okay? Chalo, let me go back and do a little bit more before we sign off for today. Okay, so that was about the introduction to symbol tables and possible connection to the activation record. Now, before getting into the activation record, the other thing that I would like to remind you of, again, I do not know if you may have knowledge of this, but in case you don't, this is the language that we'll be following. That is, the memory, as we see, it's a long array of, today in x86 it's always addressed as byte. Earlier, there are systems where people address it as word and so on, but let's take it's a byte array, very long byte array. But actually it is not that flat. It has certain segments, and these segments have very profound significance in terms of the translation process. We here are highlighting the 5 major segments the memory has. There are some more. These are the 5 major segments which are relevant for the compilation process. So the result of compilation or the requirement of runtime is memory everywhere. But depending on the type of the entity, different segments are looked at differently. For example, a memory segment called a text segment, where the program code goes. So here it is called text. This is traditional. The name text is traditional. There's no specific significance of that. But this is a program code, which naturally means that this is something which kind of is read-only. You don't expect to change the program code, right? But this is from where your program will come from. Then you have a segment where you keep your constants. So if you have some constants, particularly, for example, if you have small constants like int x or say x assigned 5. Now 5 is a constant. So it's in all likelihood this constant will go into as a part of program code itself. You'll write it as a part of the assembly itself. But if the constants are big, large, particularly the string constants, say the different format strings of printfs and so on, you do not want to keep them as a part of the program code. That's not efficient. You keep them in a separate memory segment. This is called a constant segment. And this is only for constant. So you cannot keep a non-constant value because there is hardware mechanism to not allow you to write into this memory area. The third segment is static. What it means is anything which is static, that is in C scoping terminology, anything that is global static or anything that is non-local static, that is anything static in the global scope, and any function local static will be kept here. So the static, which also actually in C means global, is the memory segment where you will have allocation for all those variables, all those symbols which do not have a function scope. Everything else has a function scope. So everything else which are within functions, parameters, local variables, temporaries, will get a binding when that function is called. Otherwise, they do not exist. But statics, which are actually globals, will exist from the very beginning of the function. Actually, they start existing before main gets called, because main may start by using some of the static variable values. It is only the non-local static, which is the function static, which gets a binding at the program beginning, but gets its initialization when the first time you execute that statement. So it's a little different semantics. So then you have heap, or which is more and more these days called free store, where if you do any dynamic allocation that is done in this area, it keeps on growing. And you have a stack, which is for the automatic variables, that is all symbols that go into your activation record, because these symbols, you don't need to manage them yourself. You don't need to do anything else. You just call the function, it happens. The function returns, it disappears, and things go in that manner. Naturally, text, const, and static, these areas are fixed. They can be changed in the operating system, but at a certain point of time, they're fixed. Whereas heap and stack are not, because it depends, you do not know how many times you'll call a function. So how many times you'll recur. So these are two flexible variable areas. So therefore, they are made to face each other. So stack grows upwards, heap grows downwards. And when they meet, you have run out of memory. So it is possible that you have very few dynamic allocation, but very deep recurring function calls. Then your stack will grow to hit the heap and you'll run out of memory. It is possible that you have very few function calls, but you have made large dynamic allocations. So heap grows and hits on the stack. Right? So this is, and traditionally the stack is taken to grow upwards. Most systems take that. So if the stack grows upwards with the memory addresses coming from top to bottom, the growth of the stack is basically subtraction. Because the address, as it grows, as you push, the stack pointer has to be decremented instead of incremented, right? So that's the segments into which things will actually happen. I think we are at the beginning of activation record. I think I'll stop here because I have. Let me see if there are any other questions. But otherwise, let me stop and we'll continue in the next class. Any other question? Is the memory segments clear? Yes. Okay then. So because I did not want to start with few things about activation record. I have another meeting I have to go. So in the next Wednesday, Thursday again, I will start from here and take you through the actual design of the activation record, which with examples of what kind of activation record layout are generated by certain systems. And I hope before that you get more familiar with the assembly language, because we will decode the activation record from the assembly code of compiled programs. Prolay, are you there?
Yes.
So you can take over if you want to proceed with something, or we will.
Yes,
can...
only one announcement I have to do. So all those who actually requested for the system in our departmental software lab, I guess that all of you got the email with the login and password information. I am working with the CIC in order to get a VPN access for you. As soon as I get that one, I will hand it over to you. Then you can log into our system from your remote place and you can work in our system. So we understand that there are some variations in the kind of flavor of Linux you are using and the systems. So in order to make it a uniform, so this is our plan. Now, since we are arranging something for you, so we request you, if there is any variation in your system, it is not at our requirement. So please use departmental system. So please use that one. In case of any problem, so the email address that I provided to you, you can directly contact to them. So VPN access, I am still working on it. So as soon as I will get that one, I will send it to you. Okay.
Good. And this presentation, I will give it to Prolay. Please share it with
yes, I will.
In the Moodle, so that
already I uploaded the theory lecture and last week's lecture. So all are there in Moodle. So I may miss to send you an email through your ERP, but as I mentioned that after the class I will definitely upload in Moodle. Please check in Moodle.
Yeah.
So you will get that one. So
I've made some changes. I'll send you this version, and you may, or you can take it from overleaf.
So our next theory class will be on Monday, and next laboratory class will be on Thursday.
And I'll continue on that. Okay.
Yes.
Thank you all very much. Have a nice day.
Second assignment will also be released in the next lab. Okay. Yes, that's it from my side.
Okay. Bye then.
Okay. Thank you.